Okay, so today I want to talk about linear programming, which is a fascinating, don't freak out, I know there's a big paragraph down there, a fascinating area of Algebra 2 and mathematics, and one of the most useful, actually. Around World War II, there were a lot of people trying to figure out how to plan for expenditures and reducing costs and trying to increase the losses that were imposed on the enemy. And a couple guys, I believe their names were Kantorovich and Koopman. They worked on this idea, which we now call linear programming, and they were so effective with it that they actually won the Nobel Prize in economics in the 70s because of their work in linear programming and the economy and transportation and stuff like that. So really, really cool application in the real world with linear programming. I want to look at a more simple example. We're not going to walk through like the World War II examples they used, but basically the idea here is that we're going to take some constraints that we have in real life and we're going to optimize the situation. And so let's just look at this example here and we'll get into it. So Lisa's making chocolate and vanilla cakes to sell at the volleyball game this weekend. A chocolate cake requires 3 cups of flour and 2 eggs. A vanilla cake requires 4 cups of flour and 1 egg. She has 40 cups of flour and 20 eggs. She can make no more than 9 chocolate cakes and no more than 7 vanilla cakes. She earns $12 for a chocolate cake and $9 for a vanilla cake. How many of each type of cake should she make to maximize profit? What is the maximum profit? And so the idea here is, look, if we had unlimited resources, she would probably just go in and make nothing but chocolate cake, right? Because she gets a little more profit for it. She gets $12 for the chocolate cake and $9 for the vanilla cake. But the problem is she is constrained by several things. So the first thing she's constrained by is flour. The next thing she's constrained by is eggs, right? She only has 40 cups of flour and she only has 20 eggs. She's also constrained by the fact that she's not supposed to make any more than 9 chocolate cakes anyway, and she can't make more than 7 vanilla cakes. So there's basically 4 constraints here. And what we're going to do is we're going to model each of these constraints with a linear equation, actually a linear inequality. We're going to shade, and then what we're going to do is we're going to look at this the solution set, which is just a shaded area on the XY coordinate plane, and then we're going to figure out which one of the corners of the shaded area creates the most optimal situation. In this case, it's going to be maximizing profit. So whichever corner results in the most amount of money, that'll be the solution. So what I want to do first here is I'm just going to zoom out and give you a preview here. We've got essentially 5 steps to the process here. And what we're going to do is in step 1, we're just going to look at, we're going to pick something for X and something for Y. And that's going to help us set up some constraints. We're going to write an objective function. So we're going to try to figure out how much money we're going to make as a function of X and Y. Step 3, we're going to write the system of inequalities that represents our constraints, right? So we're constrained by flour, eggs, no more than 9 chocolate cakes, no more than 7 vanilla cakes. We're going to graph these inequalities that we write here, and then what's going to happen is we're going to shade them in, and we're going to see that there's kind of a sweet spot, a zone that's all shaded in, and then we're just going to look at the corners of that sweet spot and figure out which corner gives us the most amount of money. Okay, so that's where we're going. So the first thing we need to do is we need to decide what X and Y are going to represent. And so what I want to do here is I want to come over and look at what the constraints are. Okay, we are constrained by the flour and the eggs. And what we're going to do is we're going to produce a certain number of chocolate cakes and a certain number of vanilla cakes. So what I want is I want that to be our X and Y. So let's let X be the number of chocolate cakes that we make. Okay, I'm just going to say the number of chocolate cakes. And let's let Y be the number of vanilla cakes that we make. Okay, so the question is how many we're going to make of each one. So generally when you get linear programming problems, you're going to want to answer that question when you're trying to figure out what you want your X and Y to represent is what are we trying to decide how much to make or how many hours to have people work or whatever. Okay, all right, so X is number of chocolate cakes, Y is the number of vanilla cakes, And now we're going to write an objective function. The objective function is just the function that's going to calculate how much money we make. Okay, so the amount of money we make is going to depend on two things. It's going to depend on the price of the products that we're selling, and it's going to depend on how many of each type of product we sell. Okay, so the prices are here. So it's $12 for chocolate and $9 for vanilla. Okay, so the question is, how much money are we going to make? Well, I'm going to say that the amount of money we make is going to be $12 times the number of chocolate cakes we make and $9 times the number of vanilla cakes that we make. So let's come over here. So it's $12 for chocolate. So our objective function is going to be $12 times the number of chocolate cakes we make, which is X. And then we're going to add $9 times the number of vanilla cakes that we produce, which is Y. Okay, this is our objective function. This is what we're going to try to maximize later when we look at the corners of our feasible region, which we'll talk about what that is. But basically, this is what we're going to try to maximize later. Okay, the next step that we need to do is we need to write a system. We need to write a system of inequalities that's going to represent every way that we're constrained. Okay, so let's go back over and look at the ways that we're constrained. So we talked about it a few minutes ago, but the first constraint we have is a constraint on flour. Okay, so our first constraint is our flour constraint. So I'm actually going to write that one out in orange here. So our first constraint is flour. And how are we constrained on flour? Okay, it says she only has 40 cups of flour. And so what we're going to do here is we're going to say, okay, well, if we only have 40 cups of flour and each chocolate cake requires 3 cups and each vanilla cake requires 4 cups of flour, then what we're going to do is we're going to write a constraint that involves, hey, I can only use 3 cups for the chocolate and 4 cups for the vanilla, and together those need to be less than or equal to 40. So let's do that. If we take 3 cups of flour for every chocolate cake that we make, and X is the number of chocolate cakes that we're making, then the amount of flour we use can be given by 3X. That's the amount of flour we use for chocolate cakes. How much flour are we going to use for vanilla cakes? If they each require 4 cups and Y is the number of vanilla cakes, then I'm going to say that the amount of flour we need for chocolate cakes is here. The amount of flour we need for vanilla cakes is there. Altogether, we need that amount of flour to be less than or equal to 40 cups. So that right there is our flour constraint. Okay, that's not the only constraint we have, though. Another constraint we have is eggs. So we have an egg constraint as well. What's our egg constraint? So a chocolate cake requires 3 cups of flour, 2 eggs. Vanilla cake requires 1 egg, and we only have 20 eggs to work with, right? She has 40 cups of flour and 20 eggs. So we only have 20 eggs to work with. So what we're going to do is we're going to say, hey, for each chocolate cake, we need 2 eggs. So the amount of eggs that we're going to use on chocolate cake is 2 times X. How many eggs are we going to use on each vanilla cake? We're going to use 1 egg on each vanilla cake. So we're going to represent that with 1Y. So 2 times the number of chocolate cakes we make is how many eggs we're going to use for chocolate cake. 1 times the number of vanilla cakes we make is going to be the amount of eggs we use for vanilla cake. Altogether, we need the amount of eggs we use to be less than or equal to 20. Okay? So that's another constraint. What else are we constrained by? There were 2 other constraints, didn't have to do with flour or eggs. Those were she can make no more than 9 chocolate cakes. So the number of chocolate cakes straight up has to be less than 9. And the number of vanilla cakes has to be less than 7. So what we'll do is we'll just come down here and we'll give ourselves a little bit of room to solve those other constraints, like the flour and egg constraints for Y. So we'll just come down here and we'll say, hey, X is the number of chocolate cakes. That needs to be less than or equal to 9, because we're not allowed to make more than that. And the number of vanilla cakes we make, which is given by y, needs to be less than or equal to 7. And so those are our constraints there. So now what we need to do, step 4, is to graph the feasible region. The feasible region is just all of the possible outcomes that we could do. You know, like we couldn't make 100 chocolate cakes and 40 vanilla cakes. We don't have enough flour and eggs for that. So what we're going to do is we're going to graph each of these inequalities, and then what we're going to see is we're going to get a shaded area that's called the feasible region. Okay, so let's actually go ahead and the easiest way to graph these is to first of all get them all into like slope-intercept form, or in a form that we can graph easily. These two are already good to go. Y is less than or equal to 7. That's super easy to graph. X is less than or equal to 9. That's really easy to graph. This one is not super easy to graph, so I'm going to recommend getting it into slope-intercept form, and then we can graph it. And then same idea with this one. So this one is not in slope-intercept form. So let's just get these into slope-intercept form. So the goal is to get the y by itself. So if we subtract 3x from both sides here, then we'll have 4y is less than or equal to negative 3x plus 40. And then if we divide by 4 on both sides, we're going to have y is less than or equal to negative 3/4 x, because we're dividing by 4, plus 40 divided by 4 is 10. Okay, so here is one equation. Okay, and I'm going to circle this, or not circle it, just kind of box it in yellow. This is one of our constraints. Okay, this is our another constraint. This is another constraint. And then we will do our last constraint here. So we'll solve for y on this eggs constraint. So if we subtract 2x from both sides, we will get y needs to be less than or equal to negative 2x plus 20. Okay, and this is our fourth constraint. So what we're going to do now is we're going to graph each one of these, and then we're going to shade where we need to shade, right? Remember, less than or equal to means below. Greater than or equal to means we're going to shade above. Okay, so all right, so what we need to do is come over, and, oh, I don't want to do that. I don't want to shrink you. I just want to zoom out. Okay, so what we're going to do now is we're just going to take each one of these and go ahead and graph it. So let's do that. So let's do the first one here. So let's do this one first. We're going to need to go up to 10, and then we're going to go down 3/4. I'm going to get like a kind of a dark blue color here to graph these. Okay, so we're going to go up to 10, and then we're going to go down 3/4. Down 3/4. Down 3/4. Okay, and then we'll go ahead and draw a straight line with a ruler here. So we'll draw that line there. And that's our first constraint. So let's go ahead and do our second constraint now, which is this guy. So we've got to do y is less than or equal to negative 2x plus 20. Uh-oh, now we have a problem. The problem is 20 is not actually on the graph here, so that presents kind of an issue. So what we're going to do here is, instead of finding the y-intercept and putting the dot up here on the 20, let's actually find the x-intercept. This is why it's really good that you understand your algebra. So if I was going to graph y equals negative 2x plus 20, and I wanted to find the x-intercept, so what I'm going to do is, instead of coming up here and plotting a point, I'm going to come down here and find the x-intercept. It's a totally equally valid way to do it. We just tend to get the y by itself, which makes finding the y-intercept super easy. The x-intercept is just when y is equal to 0. So instead of setting x equal to 0 and solving for y, we'll set y equal to 0 and we'll solve for x. So 0 is equal to negative 2x plus 20. If you add 2x to both sides, you'll get 2x is equal to 20. Which means that your x-intercept is at 10. So what we're going to do then is we're going to come over, and we should probably do a different color for this line here. So we'll do like a darker orange here. So what we're going to do is we're going to come over to the x-intercept, which is at 10, and then we'll just graph our line. So we still know the slope still works the same way. So the slope is still negative 2 over 1. So you're going to go down to right 1. Or you can go up to left 1, up to left 1, up to left 1, up to left 1, so on and so forth. And we'll go ahead and draw that line. Okay, so we'll draw that line as far up as we can. And sure enough, if we had drawn that line, it would have gone right through 20 up there. But okay, now we're set with that. Now we've got to graph x is less than or equal to 9. So we'll grab another color here and do that. Okay, so we're going to do kind of a darker green for this one. And we're going to, I'm going to move that over just a little. So if x was equal to 9, it would be right on this line right here. But since we want x is less than 9, we're going to end up shading to the left of that, okay? And we're going to save all of our shading here for just a minute, okay? And then the last thing we need to do is we need to graph y is less than 7. So we'll grab another color here. So we'll do kind of a darker pink here, and we'll do that line right there. And so now what we need to do is we need to go ahead and shade everything that we've drawn in now. So what I'm going to do is I'm going to go one by one in the same order that we drew them. So on the first equation, or to the first inequality rather, we're going to shade below that. So that first one was that blue one. So we're going to come over and I'm going to grab a pencil here and just kind of shade in below. Let's see if we can go a little lighter than that. See if we can do any lighter. So we'll shade below that blue line there. So we're going to shade below there. We'll do that shading vertically. And then the next constraint we have was this one, and that was the kind of dark orange line there. So let's go ahead and shade. We'll shade an orange, and we're going to shade below the orange line now. So I'm going to come all the way up. We'll shade everything below the orange line. We're only shading below the orange line. Notice how I'm not bothering to shade over in the negatives because we can't produce negative amount of cakes. So, all right, what else do we need to shade? We need to shade everything less than or equal to 9. And that was our green. So we'll come over and shade kind of a darker green. So we're going to shade everything that's less than or equal to 9. So that would be everything below 9. So this will be kind of shading left of the green line. So we'll shade everything left of the green line. And the last thing we need to do is we need to shade everything that is less than or equal to 7. And that was our pink line. So we'll come in and we'll shade everything. Let's do it vertically here. So we'll shade everything below the pink line here with kind of a pink color. And so now what I want to do is I want to highlight the area that we have shaded where every single one of these inequalities has shaded. Okay, so what I've done is I've grabbed a dark black pencil, and what we're going to do is I'm just going to kind of trace around the edge here. And what you'll find is that along this edge here that I'm tracing, these are all of the places where I shaded in all 4 of these. And it's this weird looking polygon, okay? So it's all in here. So it's all the stuff in here. It goes over this way, and it's got to stay below the orange line there, and it's got to stay left of that green line there. So this is what we call, this area I'm shading in right now, this is called the feasible region. These are all the places these are all the possible combos of X and Y. Remember, X and Y stand for the number of chocolate cakes and the number of vanilla cakes. These are all the potential places that we could these are all the potential numbers of chocolate and vanilla cakes we could create. So just as an example, if I wanted to, I could produce, let's say I wanted to produce 6 on the X and then 4 on the Y. This yellow point right here would correspond to me making 6 chocolate cakes and 4 vanilla cakes. Now, what's interesting is we don't really care about anything inside this inhabitable zone. For reasons that are complicated and that are a little outside of the scope of this class, we really only care about the corners. The corners are the optimal places. And I shouldn't say all the corners are the optimal places. but the corners are the places where we could potentially maximize or minimize our profit. So what I've done is I've highlighted here in yellow these 6 corners, which we call vertices. Okay, so when it says identify the vertices, these are the vertices right here. Okay, so what we're going to do is we're going to identify the vertices, and then what we're going to do is we're going to check each vertex. So vertices is the plural of vertex, which is singular. We're going to check the vertices, and we're going to plug them into the feed. So I'm reading step 5 here. We're going to plug the vertices of the feasible region, which are these 6 yellow points, into our objective function to figure out which one generates the most profit. Okay, and what we're going to do is for each vertex, we're going to take 12 times the x value and 9 times the y value, because remember, x was the number of chocolate cakes we make, y was the number of vanilla cakes we make. If we make $12 for every chocolate cake, then if you do 12 times the x coordinate, that would give you the amount of money that you would make from the chocolate cakes. If you do 9 times the y coordinate, that'll give you the amount of money that you make from the vanilla cakes. So let's go ahead and do that. So what I'm going to do is I'm going to zoom in here, and I'm going to rewrite our objective function. Okay, so our objective function was f of xy is equal to 12x, where x was the number of chocolate cakes we make, and 9 plus 9y, where y was the number of vanilla cakes we made. And what we're going to do here is we're just going to write down every vertex and try each one of them. So I'm just going to go kind of in order. I'm going to start down here, and then we'll just go this way. Okay, so we'll start down here. This vertex here is not super interesting, but the coordinates of it are 0 for the x and 0 for the y. The reason I say that's not interesting is because that's not going to return any money at all, because you're not going to sell any chocolate cakes or any vanilla cakes. Next one we're going to look at is up here. That's going to be at an x coordinate of 0 still, and a y coordinate of 7. So that will definitely make us some money. We're going to sell 7 vanilla cakes, no chocolate cakes. Is that the most optimal? Well, we'll see. So we'll try that one. The next vertex I want to look at is this one right here, which happens to be at 4, 7. So the x coordinate is 4, and the y coordinate is 7 for that one. That one looks pretty promising, because that one's definitely going to do better than this one. You sell the same amount of vanilla cakes, but you made 4 chocolate cakes as well. So we'll try that one in just a minute. What's the next vertex? The next vertex is over here. That's going to be at 8, 1, 2, 3, 4. Okay, so 8 for the x, 8 chocolate cakes, and 4 vanilla cakes. It's got some potential. All right, I'm going to scroll down here a little bit. The next vertex I want to look at is this one right here. That's going to be at 9, 2. So 9 for the x and 2 for the y value. And then the next one, which I find not very interesting because I know it's going to be worse than 9, 2, is this point right here, which is 9, 0. But we'll just put it in. 9, 0. Okay, so what we're going to do is we're going to test each of these vertices here that we've written down. There are 6 vertices. We're going to plug in the x value and the y value and see which one of these returns the highest number. So let's do that. So I'm going to come over, zoom out just a touch. All right, so we're going to do 12 times the x value. So I'm just going to come down and write these all out. 12 times the x value. So we're going to plug that x number in there. And then we're going to add 9 times the y value. So plus, 9 times the y value, 9 times the y value, 9 times the y value. And now what we're just going to do is we're just going to plug these in. So this first one here was a 0 on the x and a 0 on the y. The next one was a 0 on the x and a 7 on the y. The next one was a 4 on the x and a 7 on the y. The next one is an 8 on the x, 4 on the y. Next one is 9 on the x, 2 on the y. And the last one was 9 on the x and 0 on the y. So what we're going to do is we're just going to calculate what these are. So this would be 12 times 0 plus 9 times 0 is 0 plus 0. This next one is 12 times 0, which is 0, plus 9 times 7, which is 63. The next one is 12 times 4, which is 48, plus 9 times 7 is 63. The next one is 12 times 8, which is 96, plus 9 times 4, which is 36. Next one is 12 times 9, which is 108, plus 9 times 2, which is 18. And the next one is 12 times 9, which is 108, plus 9 times 0, which is 0. Okay, so which one of these actually returned the most money? Let's see. So the first one is 0. Next one was 63. The next one, 48 plus 63, is 111. Next one is 132. Next one is 126, and the next one is 108. Okay, if we just add those up. So now the question is, well, which one of these returned the highest amount of money? And it was the 132. It's right there. So our answer then is going to be the optimal strategy, sounds like we're playing like a board game or something, is to bake 8 chocolate cakes and 4 vanilla cakes for a profit of $132. And the 8 and the 4 came from just the X and the Y value, right? X stood for the number of chocolate cakes we were going to make. Y stands for the number of vanilla cakes we're going to make. So this right here was our optimal strategy. That made us the most money. So let's just kind of recap this whole problem here. So we'll zoom out. And so what we had was the original problem. And our first step was to figure out what X and Y were going to represent. And we decided we were going to let X be the number of chocolate cakes. Y was going to be the number of vanilla cakes. Step 2 is we developed our objective function. So the objective function was the thing that we were trying to, in this case, we were trying to maximize. Sometimes we'll be minimizing stuff. But in this case, we wanted to make the most profit. So we decided that if each chocolate cake sold for $12 and each vanilla cake sold for $9, that the amount of money we would make off of both of them is 12x plus 9y. The next step was we wrote a system of inequalities, and we did that for all of our constraints. And so what we did was we said we had a constraint on flour, and this was our inequality. It took 3 cups of flour for each chocolate cake and 4 cups of flour for each vanilla cake. And we knew that our flour together needed to be less than or equal to 40. And so we simplified it down into a slope-intercept form, which allowed us to graph it. So we did each of our constraints. We solved each of them down into a graphable form. Is graphable a word? I don't know. It is now. Then we graphed each of our inequalities. So this first one here was this dark blue one. The second one here was our orange one. The third one here was this green one. And this fourth one was this pink one right here. So then what we did was we shaded in all the regions we needed to shade. These were all less than or equal to. So we had to either shade below the line, or in the case of like x was less than or equal to 9, we shaded to the left because we wanted all the x values that were less than 9. And we got what's called the feasible region here, this black region. And it was the area where every single one of the 4 colors were shaded in. So it was blue and orange and green and pink. That's what this area was. So I shaded that in. Then we identified the vertices, which are just the corners of the feasible region. So there were these 6 corners here. And what we did was we took those 6 corners and we tested each one. We took the X and Y value of the corners, because X and Y stand for the number of chocolate cakes and number of vanilla cakes. And we tested all the corners to see which corner gave us the best result. So we plugged each corner in here. The X was the number of chocolate cakes, Y was the number of vanilla cakes, the X was the X coordinate, and the Y was the Y coordinate. And we found that the combination of 8 chocolate cakes and 4 vanilla cakes produced the best result of $132. Okay, so we said our optimal strategy then was we just decode this and say, okay, what was the 8? What was the 4? The 8 was the number of chocolate cakes, and the 4 was the number of vanilla cakes. And that's how you do a linear programming problem.